In this video, we will be talking about some different geometric interpretations and applications of measuring electric fields from different kinds of shapes. So the first one I want to talk about is electric field of a line of charge. So a line of charge we can think of as a rod with uniform charge distribution across it and conducting, so it's able to hold charge. And we would want to measure from point P what our electric field is. So in this example, we are going to be using 2 points. So if this whole section were called L, then this would be negative L half and positive L half, right, if we considered this our origin. So some important things about symmetry that we have to consider here. So if I were to draw this P over here and draw the forces acting on it, so P is considered a positive test charge point, which means when reacting to the line of charge, it's going to be deflected. So from this side, you get deflected this way. From this side, deflected diagonally this way. If we were to break out the x and y components of it, we know that since the charge is uniform and we are at an equal distance from where we are measuring from P, that means that each of these forces in the x direction are equal in magnitude but opposite in direction, which means that we cancel them out. But our y components are going to be adding because they are in the same direction. So x components will cancel, and then our y components add. All right. Here's some geometry to consider. If we called this x here, and we called this z, that means this hypotenuse, or separation of distance, is x squared plus z squared, and we would need that for our electric field equation, which is similar to our Coulomb's law, for our separation of distance, for r, right? The reason we only have one q is because we treat P as our test point charge, but because it's so small and insignificant, we do not account it into our equation. So we only want to focus on the charge that's coming from the originating object that's producing that field. Okay, so where to begin? So if we were to start by just getting an electric field for one side of P, that would look like 1 over 4 pi epsilon naught, but we don't know what Q is, right? So I'm going to write Q just for now, but there's going to be a different way we need to write it. And then over our separation distance, x squared plus z squared squared. So there's a different way that we can write Q. So when we talk about a line of charge, we are talking about linear charge density, which we represent with lambda, and that is our total charge on our object times our change in x, or our change in length. Right? In this case, our change in length will be x. So I'm going to just circle that. So if we took this and we were to rearrange to isolate for Q, so we can plug something in for our Q value in our electric field equation, we would get Q equals, just realized I wrote this equation wrong. Please excuse me. Sorry, this is going to be charge over our change in length. So now, when we rearrange, just to get Q, that's going to be Q equals lambda times change in L, which is going to be change in x for us. So now we can put this into our equation over here. All right, so that would be, so now that gives us electric field equals 1 over 4 pi epsilon 0. Then we have our new value for q, which is lambda times change in x over x squared plus z squared squared. But now we need to think about, so since we determined that we only needed our y components to add, we need to take our, we have to use geometry to find what our representation of sine theta is, right? Because sine theta will give our y component that we are looking for. So I'm going to draw this triangle over here. Where? Over here. Where? Let's put it over here. So z and x, right? We know that to find sine, we use our opposite over our hypotenuse. So if we were to rewrite sine, that would give us z over square root x plus z squared. Okay, so this is our full equation for our electric field. So now, I'm going to just simplify it a bit more. It's pi x z. Sorry, I'll draw the x better. And that's over x squared plus z squared to the power of 3 over 2. So that is our equation. If we were to measure in the middle of a length of charge from point P of distance of height z and change in length equal to x. But we're not quite done yet. So for full accuracy, we want to consider each of these sections to be infinitesimally small and adding them all up together to get that net electric field from that point P. So when we hear infinitesimally small portions, that should click something in your brain to want to integrate this. So if we were to integrate this equation, epsilon 0 so this is if it were an infinitely long line of charge, right? So our change in x, we would just get rid of it, right? So that's why change in x is missing here. And that's over x squared plus z squared to the power 3 over 2 dx. Our integration limits are what we defined over here. So that would be from L over 2 to negative L over 2. I'm not going to show the full process for how we get there. But just know that once we integrate this, this turns into 1 over 4 pi epsilon naught lambda over z and L over length for 2 squared plus z squared. So length over 2 is just in place of our x because that is what we are integrating with respect to. So that is the equation that we would use for that case. So like we mentioned, so in a limiting case, so as line of charge is infinitely long, so we're going to just take a look at this bottom term right here. I'm going to highlight this. Oh, won't let me. Okay, it's fine. I'm just going to circle this right here. this term over here, so as our length becomes infinitely long, compared to our z, this is going to be a much larger term, because if we were to write this, so that's like saying if our length was infinitely long, so that's like saying infinity over 2 squared plus z squared. Compared to this is a really, 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 really big number. So that's like if you had like $1 million versus like $1,002,000, right? You can kind of just equate it to having $1 million, right? So that's why this x is negligible. Sorry, z squared negligible. In comparison to our length. So in that case, our equation for electric field will just simplify down to so that's L over 2 squared. Simplify it down even more. So that's L over L squared. Cancel those L's. So finally, that will give us, I'm going to do this in a different color, 1 over 4 pi epsilon naught lambda over z. And that 2 from up here, so that we're going to move that 2 up here. That's going to cancel with our 4 and reduce that 4 down to 2. So this goes away. And that brings us down to 2. So this is our final equation that we can use if our line of charge is infinitely long. All right, so next we're going to use an example of an electric field of a ring. So now what do we do if we have a ring and we want to find the electric field at a point above that ring? So let's sketch that out. Where our point is at a distance of z, we have a radius of r, and we have our separation distance, which we can write out really quickly. We know that to be r squared plus z squared, square root, right? So when we are taking the electric field of this, we want to consider breaking up our ring into small little arcs, right? So say we use this little arc right here. That's going to have angle phi. So our electric field, similar to our previous question, is going to need a change in Q over our separation squared. And what angle do we need to add to it? Well, that's a good question. So let's talk a little bit about our symmetry that we might see here. So our z components are going to add because our x and y components are going to cancel. So it's the same kind of thing. Both of these add, x cancel, and so do our y components, but that's kind of difficult to draw in this space. But you can imagine from a top point of view, so if this is our ring, right, that it would be deflected like this, radially, right? So all of these are going to cancel out, and it's only going to leave our z components. X, y cancel. So that means we'll be attaching a sine theta to that because we need to add up both of our z components. Okay, just like the last question, we know that linear charge density is equal to Q over L. In this case, Q be equal to 2 pi r, because that is equal to our circumference. But when we rewrite it, this is just for our small arc. So we want to just only consider our small arc. That's why I wrote this down over here. So that's what we're going to be using in place of Q. So when we write our electric field equation out, let's make our brush smaller. 1 over 4 pi epsilon naught. In place of Q, we have lambda r times change in our phi, and that's just for our small arc over here. So rather than using our whole circumference, we're just going to use a small arc. So this is what's in place of our 2 pi r over our separation distance of r squared plus z squared. And now we need to think about our sign. So using our knowledge from the example we did previously, we know that that is going to be, so if this were our theta, it's going to be z over r squared plus z squared. We simplify that, that becomes r squared plus z squared 3 over 2. So there is our electric field. And we can stop there. So there it is. And we are done for that part of the question. Now we're going to be taking a look at the electric field of a disk. Sorry, there was a part that I missed. So for a limiting case for our ring, so as each section becomes infinitely small, we treat our phi, our change in phi, as derivative of phi. So when we write this out in our equation, that means we have our electric field. Actually, no, sorry. Before I write that, because we're looking at infinitely small sections, that means we'll have to integrate our equation. So then that's pi r z over r squared plus z squared to the 3 over 2. And we are integrating from limits 2 pi to 0, right? Because when we have our whole circle, we want to go around the whole thing from 0 to 2 pi. So when we write this out, that will give us our z to 2 pi 0 r squared plus z squared to the power 3 over 2. Right? And then we're going to plug in this for our value of phi. So when we do that, we have 1 over 4 pi epsilon 0 r z. And in place of our phi, I'm going to do this in a different color. We have 2 pi squared squared plus z squared to the power of 3 over 2. And we know from our linear charge density equation, so let's just write that out again, over length equals q over r circumference, 2 pi r. Then when we isolate for our q, we have lambda 2 pi r. We can locate those terms in our equation right here. Together, those will go to create our final equation, which is 1 over 4 pi epsilon 0. In place of those terms right there, we have our q times z, r squared plus z squared to the 3 over 2. So there's our final answer for our limiting case for a ring. So now we're going to talk about the electric field of a disk. So when we worked with our ring of charge, we treated it essentially the same way that we treated our line of charge. But now what happens when we are replacing our object with a full, dense object, like a disk? Well, then things change a little bit. So now considering that we have a disk, there's a new value that we will need to define, and that is surface area charge density. So that is given by sigma equals charge over area. So when that happens, if we isolate for q, that's sigma times a, and our area of a circle, pi r squared. And rather than writing r squared, we're going to use q equals density r times change in r. Okay, so we're going to use the same geometrical process that we used for our ring. Same kind of deal, right? So this is z squared plus r squared. I'm going to go a little quicker through this one since you guys already kind of used to how we did it. I'm going to plug this in for our q. And that's over z squared plus r squared, power of 3 over 2, in the k direction. Sorry, I forgot this one other thing. There you go. So in our limiting case, so the way that we break this out to integrate it, we are breaking them out into smaller and smaller disks, right, where each one adds to that electric field, that net electric field pointing upwards at P. So in our limiting case, as delta R approaches infinity, oops, sorry, nope, this is wrong. So as each section is more narrow, our change in R is just going to be denoted to dr. So when we integrate this, again, we are integrating from R to 0, right, where R is the measure of the whole thing, 0 is the center of it, so we're using each consecutive ring. And that's 2 pi r times z, this. change in r becomes dr. Then we have r squared plus z squared over 3 over 2. And when we integrate that, that gives us 4 pi epsilon 0. All of this is constant, so we're going to kick this out of the integral. And that leaves -1 over square root r squared plus z squared from r to 0. And finally, we see that this will reduce down to 2, so that's 1 over 2 pi epsilon 0. Linear charge density, it's 1 minus z over r squared plus z squared in the k hat direction. Another limiting case is r is equal to infinity when z is close to disk. So think about like when you're in an aircraft. When you're in an aircraft, your city looks a lot smaller, but when you're on the ground, it looks a lot bigger, right? So that's why if we were to have our point z measured from 0 at a height of 0, our radius is going to look a lot bigger to it. So in that case, if we were to rewrite this equation that we just derived, 1 minus z, in place we had infinity on the bottom, right? So that's like saying like 1 over super big number. That's going to give you a really small number. So we say that this is close to 0. In that case, we cancel this out, that whole term. So now we are just left with linear charge density over 2 epsilon 0, and our pi will cancel out in the k direction. So it's going to be a really important equation, so make sure you hold on to this. It will show up a lot in exams. Next, we will be talking about parallel plates in electric fields. So something you should know about parallel plates. So as the name suggests, they are two parallel plates who carry the same charge with opposite sign. So same charge, opposite sign. So that means everywhere within the parallel plate region is going to have uniform field. We know from our electric field diagrams that it flows from positive to negative. So we will draw those arrows as such. Yeah, so these were a really significant tool when we were first coming up with ideas of electrostatics, because when we observed particles moving through it, we noticed that they could be suspended depending on the charge of the particle. And a scientist by the name of Millikan was able to use these tools. I think his name is Robert, first name, probably. Robert Millikan used this tool to find the charge of to find elementary charge of the drop, of an oil drop, right? So he used really, really, really small drops of oil and suspended them in this parallel plate field. So how would you do that? So we know force of gravity always wants to pull a particle down, right? So you would have to ensure that your electric force electrostatic force, pulled it in the opposite direction at an equal force. So if we put this particle in here and we wanted it to move towards the positive, right, for our electrostatic force, that means this would have to be negative, right? So that's how we found the charge of an electron back in the day. So that means that our electrostatic force would have to equal our gravitational force in order for it to stay suspended. So if we were to do a quick example of this, right, I'm just going to use this drawing up here because I don't really feel like drawing it again. But say we had a particle moving through and it got deflected. So our information that we're given, our oil drop is 1.7 times 10 to the negative 10 kilograms. Our Vx is 20 meters per second. Density charge is 26.6 meters squared at 1.5 centimeters. So we want to find charge. So we are going to be introducing a new equation, which is electric field between plates, which is E equals negative charge density over epsilon 0. So when we use that to solve this question here, that gives us electric field equals negative 0.85 times 10 to the negative 12. And that gives us, so we're given that, so that's negative 26.6 times 10 to the negative 6 for our density over 8.85 times 10 to the negative 12 equals our electric field of negative 3.01 times 10 to negative 6 per coulomb. Oops. No, stop. Get out of here. Okay, so I'm sure some of you are already figuring out what we are doing to be able to solve this. So first we're going to find electric field. We're going to use electric field to find electrostatic force. Then we're going to use our motions to equate our forces. So that was step 1. So now moving on to step 2. We want to find our x direction acceleration, so x direction, and y direction. So we can find the distance that it's going in the x direction. So we're going to use that first. So distance that it travels in x direction. So we have Vx over dt. We want to find d, so that's d equals Vx times t. That's going to give us, when we have kinematics questions, we want to find time, right, and use time to relate the two. So that's going to be t equals d over Vx. It's going to equal 0.015, right? That's from there. Vx, 20 meters second. That gives time of 7.5 times 10 to the negative 4 seconds. We're going to put that into our y direction to find what our y velocity is. So d over t. And we know that it gets completely deflected all the way up to the top. We just need to find the separation. But there's actually a different formula we can use for that. since we aren't given that. So instead, we will be using dy equals 1 over 2 yt squared, and that gives dy equals, vy. Is that right? Nope. Sorry. We want to find our acceleration. I'm so sorry, because we want to use that to find our opposing force. So we are looking for acceleration. So that becomes 2. This is 6 times 10 to the negative 4. Over our time, which is 7.5 times 10 to the negative 4 seconds squared. And that gives us 1,777.78 meters per second squared for acceleration. And finally, we want to, running out of room right here. It's okay. Lastly, we want to find what our force is and what the charge is. So we know that our forces must repel, right? So M-A-Y, so this is our gravitational force, or one of the forces. And we know Q times E is equal to our electrostatic force. So I'm going to color these in. So according to our diagram up here, so our left side represents our downward force, or upward force rather, and this represents our electrostatic force. So when we solve for Q, Q equals M times AY divided by our electric field, which equals 3.02 times 10 to the negative 7 newtons per, which we solved up here, newtons per coulomb. Right, that's where this value came from for our denominator. And that means our charge is negative 1.6 times 10 to the negative 13 times 10 negative 13 coulombs. It's not quite accurate, but you know what? It's not bad for our charge of an electron, or of an oil drop rather. So that's how you can use your knowledge of force equilibrium to find certain values for parallel plate questions. All right, so that brings us to the end of our notes review for deriving different equations for different geometric applications of finding electric field. In the next video, I will be going over some examples that include these equations to help solve some practice questions relating to electric fields. Thank you for watching.